Hi everybody. We're going to take a look at guided notes for standard 10 patterns, and we're going to start with two different activities. So our part 1 activity says, how could you find the sum of the first n odd counting numbers without actually adding them? Fill in the table and see if you can discover the pattern. So beneath here I have a table and I also have a figure. In my table, we're looking at our first n odd counting numbers. And so the n represents our first odd counting number, our first 2 odd counting numbers, our first 3 odd counting numbers. And then the sum column looks at us adding up those odd numbers. So if we think when n equals 1, or what is our first odd number? Our first odd number is 1. And if we look at the figure also depicts that. So if you look at the bottom left corner of the figure, you can see our first odd number is 1. Well, for the sum, we're not adding anything yet, so our sum is just 1. Our first 2 odd numbers would be 1 and 3. And if you look at our figure, we can confirm that. Our first odd numbers here are 1 and 3. For our sum, we need to add 1 plus 3 to get 4. Our first 3 odd numbers are 1, 3, and 5. We can double check in our figure. 1, 3, and 5. When I add 1 plus 3 plus 5, I get a sum of 9. And you can continue on. So at this time, I'd like for you to pause the video and finish filling in the table for our first 4, 5, and 6 odd numbers. All right, here's what I came up with in my table. And you can see for n equals 6, I listed my first 6 odd numbers. When I added up these 6 numbers, I got a sum of 36. I could continue filling out my table when n equals 7, 8, 9, etc. However, what if I was asked to find the sum of the first 100 odd numbers, or to find the sum of the first 1,000 odd numbers? There's no way we would take the time to list all of those odd numbers and then add them up to find their sum. So instead, we need to find the pattern. And that's why it's helpful that we listed this in a table so that we can try to find a relationship to write a rule, a generic rule using n for our sum of the first n odd numbers. So we're going to try to look for the relationship between our first column, n, and our last column, the sum column. So if we look at when n was 2, our sum was 4. When n was 4, our sum was 16. When n was 5, our sum was 25. Maybe you're starting to notice a pattern here, and that pattern is that you're looking at n squared, or 4 squared, or 4 times 4 is 16. 5 squared is 25. 6 squared is 36. So that's our pattern. We're doing n squared, or n times n. So our rule here for the pattern is n squared. However many number of odd numbers we're looking at, we're going to square that, and then that would be our sum of the first n odd numbers. So here's our first pattern that we were able to come up with. And we came up with this again by filling in our table and using some critical thinking skills to try to catch the pattern. Now let's take a look at part 2, which says you are given the figure at the right, which is built entirely of squares. The area of square C is 64, and the area of square D is 81. Use this information to determine the area and side lengths of all the other squares. So first I'm going to start by listing my given information. So I was given the area of square C is 64. So I'll jump to my table, find square C, and list the area as 64. I was also given the area of square D is 81. So I'll go to my table, and for square D, I'll list the area as 81. So this is what was given to me, but we know a relationship between the area and the side length of a square. So let's talk about that relationship. In a square, all of the sides have to have the same measure, or they have the same side length. So in a square, if the side length is S, and you want to find the area of a square, you would do side times side, or you would do side squared. For square C, if my area is 64, I need to think backwards or work backwards to find the side length. So one way I could think about it is because the area 64 is my side times my side, I could think what number times itself gives me 64. Or I could think to undo the side squared, I would have to take the square root. So I could take the square root of 64 to get 8. Or I could think 8 times 8, or 8 squared, gives me 64. Similarly, for square D, I could take the square root of 81 to get 9. Or I could say 9 times 9, or 9 squared, gives me 81. This is helpful because now that we know our side lengths, we can label them in our figure. So for square C, I will list all of my side lengths as 8. And for square D, I will list all of my side lengths as 9. And now we need to use some critical thinking skills to be able to work through this figure to label all of the side lengths so that we can list them and find their corresponding areas. So right here I see this tiny little square I, and I see that the side length for square D is 9, and the side length for square C is 8. So if I see that square D has an overhang here, the difference between 9 and 8, or when you do 9 minus 8, we get 1. That represents this little overhang, or that represents the side length here for square I. So if square I has side lengths of 1, I can jump over to my table and fill in 1 for the side length for square I. And then for the area, I can do 1 squared to get 1. From here in my figure, there are different ways you could go about it. One approach, I might try to now find square E, or instead you could try to find square H next. I'll try to find square E. So if my side length for square D is 9 and my side length for square I is 1, I need to add those two side lengths because I see that the side length of D plus the side length of I forms my side length of E. So when I do 9 plus 1, I get 10. So my side lengths for square E are 10. Jump over to my table, fill in 10 as my side length. And then for my area, I do 10 squared to get 100. So you're going to reason through this figure and try to come up with the side lengths in order to find their areas. So go ahead, pause the video and see what you come up with. All right, here's what I came up with. So I'll give you a moment to look at my table and look at my side lengths and their corresponding areas. Let's jump over to the figure and talk about some of the trickier parts of the figure to crack. So I'm hoping that square H and square B were a little bit easier. In my opinion, square G was the trickiest square to figure out. And in order to find square G, you had to look at the relationship here between squares E, H, and I. So I see that the whole way across square E, the side length is 10, and the side length for square H is 7. I see that the square H has this overhang here of 1. So if I'm looking at just the distance right here, well, if the whole square H is 7, but it has this overhang of 1, then this little piece here must really be 6. So if I'm now trying to say that this portion of the side length in square E is 6, and we know that the whole side length in square E is 10, if I did 10 minus 6, that's how I would get the side length of 4 for square G. So then once you know square G is 4, then you could add up side lengths for E and G to get F, and then you could add up side lengths of F and G to get A. So really, this square G was the trickiest one to crack. Very last part of the front side of our notes says, is the overall figure a square? And in order to answer this question, we had to reason through the figure, find the side lengths, find the areas. So what must be true if the figure is a square? Well, we already said if the figure is a square, it has to have the same side lengths. So we could reference our figure and we could try to say, what is this side length measure? on the bottom of the figure, and also what is this side length measure? Because they must be the same if it is a square. So across the bottom, when I add 14 plus 10 plus 9, I get a sum of 33. So the overall, the big square has a bottom side length of 33. I could double check here going along the left side when I do 18 plus 14, or over here along the right side, I could do 15 plus 8 plus 9, and I get 32. So my left and my right sides of this square are 32, and across the top and the bottom, my side lengths are 33. So if I have two different side lengths, can the overall figure be a square? The answer to that is no. All right, on the back side here, it says, what is a proof? And we're going to define some of these terms. And actually, this is going to be foreshadowing for when we get to standard 12 proofs. So to define the term postulate, and we've seen this term before, a postulate is something we assume to be true but cannot prove. Something we assume to be true but cannot prove. Proof is evidence that something is right or wrong. Evidence that something is right or wrong. You could also say evidence that something is true or false, evidence that something is correct or incorrect. And then we have two different types of proofs that we're going to look at. So a free-form proof is free. It has no structure. There's not a set structure to use, but it does give an explanation why. It gives an explanation why. And you can think to the front side of our notes where we were working through some patterns. So I always like to say free-form proofs, often you're looking at patterns. And when you're looking at these patterns, you don't have a set structure, but you are able to give an explanation why something is right or wrong. Versus a formal proof, and I like to think of this as, we're going to do a ton of this in standard 12 proofs. And these ones definitely do have a structure. And the structure is called the two-column proof format. So these are going to be two-column proofs. And we'll see an example of them below. Which is more valid, a free-form proof or a formal proof? And while you may think that a formal proof, because it's got all this structure, it would be more valid, but really that's not the case. Both are valid. They're just different ways of providing an explanation. For a guided practice, example A says, solve the following equation using a formal proof. And I'll point out that here we're doing a formal proof, and in your U-Try you'll be doing a formal proof. And when we get to standard 12 proofs, we will do many two-column proofs. So the two-column proof format has one column with statements and the other column with justifications, or you could say the reasons. The first step when setting up a formal two-column proof is to list what's given. So in this case, we are given the equation 5x plus 4 equals 24. So I will list that for my statement. 5x plus 4 equals 24. My reason or justification is simply that it's given to me. I am told that it is given. Now I need to go through solving this equation. So think back to algebra. I want to get x by itself, or I want to isolate x. So I need to first undo this plus 4. I need to do the inverse operation here. So I need to minus 4 from both sides. So I will get 5x equals 20. And my justification for that is called the subtraction property. I'm going to just put subtraction prop for short, but we subtracted 4 from both sides. Now I'm still trying to get x by itself, and this is 5 times x, so I need to do the inverse of multiplication, which is division. I need to divide both sides by 5. So I'm left with x equals, and 20 divided by 5 is 4. So this reason is called the division property. And again, I'm just going to abbreviate division prop, but all we did here was divide by 5. And then we proved that x equals 4, and we're used to working out our equations like this. The new piece is that in this 2-column proof format, we are giving the reason. What is the name of the property that allows us to do these steps to find x? So at this time, go ahead, pause the video and see what you come up with for you try 1. You can check how you did on you try 1. My first statement was writing the equation. My justification was that it's given. And then I had to add 8 to both sides, so it was the addition property. And lastly, I had to divide by 6 on both sides, so it was the division property. If we look at example B, it is now a free-form proof. And you try 2 is a free-form proof. So at the top, that is where we're looking at patterns and we don't necessarily have a set structure. So similar to what we did on the front side, right? We might have figures, or we're using our critical thinking skills to be able to fill in a table and find the pattern. So if we look at, we have some figures and we see that when n is 1 here, it's actually referring to the number of squares in figure 1. When n is 2, we're trying to find the number of squares in figure 2. Here would be figure 3 and figure 4. So that's what the n here is representing, our first, second, third, and fourth figure. We have to fill in this table because at the bottom of the table, you can see that we need to be considering the 200th term or the 200th figure, and we only have 4 figures. So we're going to have to, like we did on the front side, come up with a generic rule for n, for the number of squares, so that we can apply that rule so we can know the number of squares for the 200th term. So when n is 1, I can count my squares in this figure, and I can count that there are 8 squares. When n equals 2, or my second term here, I can count the number of squares, and I have 16 squares. When n equals 3, I can count the number of squares, and I have 24 squares. When n equals 4, count the number of squares, and I have 32 squares. So by listing the number of squares in my table, I now need to observe what is happening. Is there a pattern happening here? What exactly is the case? So one way I could notice is that in each instance, I am multiplying my n by 8. 1 times 8 is 8. 2 times 8 is 16. 3 times 8 is 24. Another way to look at it is to look at it this way. And my common difference here between all of these numbers is 8. I'm saying 8 plus 8 gives me 16. 16 plus 8 gives me 24. 24 plus 8 gives me 32. So this number here, this is called the common difference. Common difference. And this is the number that we can put in front of n. So when we find the common difference, these numbers 8, 16, 24, and 32 have a common difference of 8. And this is the number that we can put in front of n. So to write our generic rule, we could say that we're doing 8n. 8 times 4 is 32. 8 times 3 is 24. Now that we have a rule that works, we can figure out what the 200th term in this pattern would be by plugging in 200 for n. So we could do 8 times 200, and we would get 1600. There would be 1600 squares when we look at the 200th figure, or the 200th term. So go ahead at this time, pause the video, and see what you come up with for you try 2. Here's what I came up with in my table, and I noticed that here my common difference was 4, but I couldn't just write 4n for my rule, and you could test it. Is 4 times 1, 1? No, 4 times 1 is 4. Is 4 times 2, 5? No, 4 times 2 is 8. So you'll notice that at the end of my pattern, this one was a little bit trickier, I put a -3. Why did I add this? Because when I look at n equals 1 and I plug in 1 for n, 4 times 1 is 4, but it should be 1. So by adding the -3, 4 times 1 is 4, -3 gives me 1. When I look at n equals 2, or I'm plugging 2 in for n, 4 times 2 is 8, -3 gives me 5. 4 times 3 is 12, -3 gives me 9. 4 times 4 is 16, -3 gives me 13. So I had to try to find what number here, and it could be plus a number or minus a number, that I can attach to my common difference times n to get my pattern to work. So this was a tricky one, but we'll practice this plenty in class. I have to find still what will be my 200th term. And so I can do 4 times 200 minus 3. 4 times 200 gives me 800, minus 3 gives me 797.